Okay. Last class we concluded with 3-phase midpoint configuration and the firing angle range for inductive load. Now, let us take the discontinuous operation of this 3-phase midpoint configuration. This will happen when you have resistive load. This is for understanding the firing scheme and how the converter works. So, operation with resistive load, with resistive load. We are talking about 3-phase midpoint configuration. So, the 3-phase midpoint configuration that last time we have drawn, it will be E1, E2, E3. This is our neutral, E1, E2 and E3. Okay. Then you have the small leakage inductors take care of the finite on and off durations, so that we can avoid the dead short circuit between phases. This is our highly inductive load. Okay. Now, in this case, suppose the load is resistive, that means resistive. Load is resistive. In that case, what will happen? Let us draw the 3-phase waveform. This with practice you can do it. A phase, this is the B phase, then this is the C phase. Waveform is not as okay. This okay. This is our E1, this is our E2 or E3, it can be there. Now, last time we told that the firing angle starts from here, alpha is equal to 0 here, and there are 3 devices. So, each device will be conducting for 180 degree, 120 degree. So, alpha is equal to 0, this is the envelope, that is the E1 envelope coming across the load when alpha is equal to 0. Now, let us take when alpha is equal to 30, that means alpha is equal to 30 is, suppose it is next phase we are going to switch on alpha is equal to 0, or A phase is going to switch on alpha is equal to 30, that is here. Alpha is equal to 0 here, this alpha is equal to 0 here, alpha is 30 here. Then what will happen? Immediately go here, it will come here like this. Okay. Again the next phase starts here. So, it will for resistive load, if you see here, the voltage or the current waveform will be in phase with the voltage waveform. So, if slightly voltage goes negative here, it is not possible here, because there is no inductive load. So, the inductive current dIu dt cannot change, the slope cannot change, and we cannot force the thyristor in the on state. So, here immediately the moment voltage comes to 0, resistive lead current will also come to 0, because voltage and current are in phase, the thyristor will switch on immediately here. But for voltage control alpha, we can, as I told before, alpha can go from 0 to 180 degree. Now, let us take alpha more than 30 degree. Alpha more than 30 degree. So, I will again redraw for clarity. This is our A phase, this is our B phase, this is our alpha more than 30 degree, alpha 30 here more than let us take at this portion. So, the envelope will be like this. At this point the commutation stops, the current the thyristor switches off, but the next thyristor again will be turned on here only. So, the voltage ripple coming across the load is different from that of an inductive load. So, this is the portion. What it shows, with the resistive load, there is a discontinuous conduction depending on the firing angle. That means alpha more than 30 degree, there is a discontinuous conduction. Now, what will happen when alpha is, as the alpha increases, the ripple part, the input mains, part of the mains coming across the load will slowly get reduced. At alpha is equal to 180 degree, the output ripple will be coming across the load is 0. That means output voltage is equal to 0. So, this way also resistive load, we can have a 0 to positive voltage variation possible. Now, see, is it only possible with resistive load? Can we have a discontinuation with discontinuity occurrence with an inductive load? It is possible. That means, when the voltage waveforms goes negative, we should give alternate path for the inductance, so that instead of forwarding the thyristor and the current flowing through the thyristor, it can free wheel through another path. So, it is possible. Suppose the load is inductive. See, if you give a diode like this, this is inductive, load is inductive, and with the diode, the moment the voltage waveform, this is positive, it can only positive, and any time it is negative, what will happen? Current will free wheel through this way. Okay? This is possible. So, we can, this way we can ensure, suppose the output voltage we want to limit it, only, we do not want output DC voltage or instantaneous voltage, we need not want to go to negative, we can use a free wheeling diode. So, that and with the firing angle variation, we can have a output voltage variation from 0 to positive. Now, here what will be the output DC voltage equation with respect to the firing angle, that we can find out here, that is E0 alpha. Again, for a general m phase, it will be 1 by 2 pi by m. So, m by 2 pi integral. So, integral lower limit and upper limit depending on whether you are taking sin omega t or cos omega t. So, let us take Em, maximum value of the phase voltage, and cos omega t d omega t. That means, we are finding the area in a period and divide by the period, that will give the average value, that will give the DC value. Now, what will be the lower limit? Sin omega t means, cos omega t means here. So, firing angle minimum is here. So, it will be this distance from here to this distance. This will be for a 3 phase it is pi by 3, for m phase it is pi by m. So, lower limit is if omega t is equal to 0 here, 0 here, omega t is equal to 0 here for cos omega t waveform. So, when we go to the lower limit, it will be minus pi by m, then plus alpha. So, alpha can vary from 0 to, that is from here to here for symmetry operation. That is that we have studied in the last class for a general inductive load. But for a resistive load, the upper limit is for a cos omega up to here. Below that, output ripple is not coming across the load, discontinuous conduction. So, upper limit is pi by 2. So, if you do the integration here, finally you will get m by 2 pi into Em into sin omega t minus pi by m plus alpha upper limit pi by 2. So, final equation in terms of RMS value root 2 E, here E is the RMS value m by 2 pi into 1 minus sin alpha minus pi by m. This is the general equation. So, for a 3-phase waveform, for the 3-phase case, 3-phase midpoint configuration with a resistive load or inductive load with a freewheeling diode. Why freewheeling diode? We require the thing to go through the diode only. The output ripple waveform will be 0 to positive or negative, it will not be going. We can plot it. This will be for a 3-phase case. For the 3-phase case, from the previous equation, that is E0 alpha, it will be equal to root 2 E divided by 2 pi into m into 1 minus sin alpha by pi by m. For a 3-phase case, we can put all m is equal to 3. So, the curve approximately will be something like this. At omega t is equal to 150 degree, you will have start discontinuous conduction. Maximum will happen alpha is equal to 0 degree. This is E0 alpha by ERMS. E0 alpha by the maximum value. That is, what is the maximum value? ED0 maximum here. Okay. So, when you do it, it will go like this. Now, we have studied about 3-phase midpoint configuration. Now, again for high power applications, also to increase the output DC voltage and also to reduce the ripple content, that means increase the ripple voltage, we have to go for 3-phase fully controlled converter. That means it's same like single phase fully controlled converter, we have to go for the 3-phase fully controlled converter. So, now we will start studying about the 3-phase fully controlled converter, that is 3-phase or 3-phase bridge. 3-phase bridge. So, how the configuration will be for the 3-phase bridge? Let us start studying about the 3-phase bridge. 3-phase bridge, here same like 3-phase half control bridge, we will be rectifying the waveform during the negative portion also. So, this can be written like this to start with. This is our previous positive side. Okay. We will, for making the figure clarity better, so we are removing the inductance now. We have the mains here, E1, E2, then E3. Okay. This will go here. Okay. As before, cathodes are connected together. Now, we want the negative portion also. So, what we will have? We will connect diodes like this. No, sorry, thyristors like this. 3 thyristors. So here the cathodes here are shorted together. So what will for negative here we will anodes are shorted together. So the load will be across this one. And it will be connected here. Now what will this side, this would again it will be connected to E1 side. What will happen? This will go to the E2 side. Then this E3 will be connected here. Okay. This is the negative side also. So we are from the analysis from the positive side, we are extending to negative side. Negative side also you want to conduct, the thyristor to conduct, and current conduction, that is current will conduct in this direction. That will be, even though that will be done through the inductive load, it will force through this one. Now in a simple way we can again, but this way it this is the way the way it extends from positive side to negative side. Now, but if you see the actual rectifier in any textbook, it will be like this. That means this the same connection in a simple way we can represent like this. 1, this is for the positive part and this is for the negative part, and here is our load. E1, E2 are here. E1, E1, E2 is this way, E3 is this way as before. This is the neutral point, that is this point. So this is the extension of this one. The concept, the negative side also we can use it the same way, in an opposite way the thyristor has to be connected, and this the 3-phase fully controlled configuration can be derived this way. Now let us see what is the firing angle range and where the alpha is equal to 0, what is the output waveform, output DC, output ripple, and also the output DC with respect to firing angle. We will study now. So let us go to the next. So we will rewrite the previous figure again here for clarity. This is the positive side, this is the negative side. So we are trying to make use of the input waveform for power transfer during the positive as well as negative side. So maximum utilization of the 3-phase means. E1, E2, E3, load is here. Okay. E1, E2, E3. This E1, E2, 3 can be represented as ABC or RYB. Okay. Now, how the commutation starts? What is the sequence of switching? If you see, there are 6 thyristors now. Okay. And in a cycle of operation, that means TS period, the period, fundamental period is equal to T, is a 360 duration. So each thyristor, the conduction duration for symmetry operation, the conduction duration for each thyristor will be 6 means how much it will come? It will be equal to 60 degree. See, each thyristor will be conducting total only 60 degree duration in a 360 period interval. Okay. Now, previously when we discussed about the top and bottom, each thyristor for the half bridge cone, for each thyristor will be conducting for 120 degree, and every 120 degree there is a commutation process initiated. Now, here how it will happen? Let us first draw the 3-phase mains waveform. All these phase control converters using thyristor, these are natural commutation. That means the incoming thyristor will force the previous conduction thyristor by applying the reverse voltage across it from the incoming phase. So, let us draw the 3-phase waveform. This is our A phase, 120 degree, you will have the B phase, then 360 degree you will have the C phase, or even E2, E3. So, this is E1, this is E2, this is E3. Now, alpha is equal to 0. Let us take E1. When the E1 phase is at this instant, if you see here, E1 from, if you take our omega t is equal to 0 here, omega sin omega t, you are starting from here. Let us take for E1 to turn on, the positive, E1 is positive here. So, from this point to this point, for the positive side, if you see here, E1 will be conducting. No, sorry, E1 is positive and T1 will be conducting. So, this is T1. So, this is positive, this is T1. Okay. So, E1 will be conducting. Now, E3 is here, if you see here, E2 is more positive from this point to this point. Sorry, E2 is more negative. So, the thyristor which is maximum negative, E2 negative. So, that will be conducting now. So, we have initiated the firing angle from here, that is initiated the firing angle process alpha is equal to 0 from here. Now, from here to here E1 will be conducting, but at this point, after that this point E3 will become more negative. E3 is more negative means the next thyristor to be turned on, first one is turned on, next is this is T2. So, this duration is for T2. So, E3 negative. So, this is T2, next is T2. See, as I told before, see the positive side and negative sides are independent of each other from the previous diagram. So, as before, the conduction duration for the upper limb as well as the lower upper limb is 120 degree, not 60 degree. So, this is 120 degree, not 60 degree. But if you see here, every 60 degree, see, there is a commutation. That means there is a new thyristor turned on. This is T2. Now, at this point, so we are turning on alpha is equal to 0, we are turning on T1 here, then at this point we are turned on T2. Now, upper limb E2 is going more positive. So, T1 should be switched off and T3 should be turned on. Next is T3. So, this will be T3. This is T3. This is T3. Okay. So, but at the lower side here E1 will become more negative. So, here it is T4, even more negative means T4 means here, this is T4. Okay. Now, again E3 become more positive here at this point. At this point T4, T1, T2, this is T4, this is T3, E3 become more positive. E3 become more positive here, no sorry, at this point E3 become more positive. So, which one has to be turned on? Now, T4 is our next thyristor, we will name as T5 here. Then here E2 become more negative after 60 degree, that is T6. This is T6. So, we will again draw the waveform and the conduction duration again we will write for clarity. So, let us go to the next page now. See, we will this is one thyristor, we will make it bigger. Okay. Okay. Then so each phase will have a positive and negative part, and these can be independently triggered also, as I told before. These are independent because this is the positive half bridge, this is the negative half bridge. Now, this is the E1. E1 here, next one E2, next is E3. This is our neutral. E3 here. Now, let us draw the phase waveform again. This is E1, 120 degree you can have approximate. E2, now we can have E1, E2, E3. Okay. So, our alpha is, so we will try to understand again for alpha is equal to 0. So, E1, this is E1, the first one is E1, that is this one, E1, this is E2 and this is E3. Now, alpha is equal to 0, we are firing here. At alpha is equal to 0, E1 is more positive, so thyristor 1 is fired. So, E1 side positive, this is E1, this is E1, the positive side thyristor will be this one, that is T1. So, T1 conduction duration will be this period. Up to this period T1 will be conducting. Then only the next positive side T2 will conduct. So, T2 conduction where? This is the T2 conduction period. At this point we will be initiating T2. But if you see the negative side, that is this portion, if you see here E3 is more negative, after E1 is more PCT, E3 will become. So, for each phase whether positive or negative limbing at the same firing angle alpha alpha is equal to 0, we have to use for the positive or for negative. So, positive alpha is equal to firing angle here, for negative the firing angle alpha starts from here, okay. Negative firing angle alpha, that from there the phase become maximum negative. Here the maximum negative will be E3. E3 will be maximum and negative. So, here on the T2 thyristor will be conducting. This is T2, okay, T1, T2. Now, E1 is still conducting. So, at this point E1 and E1 phase is more positive, T1 will be conducting and T2 will be conducting. Now, at this point E2, the phase E2 become more positive. So, T1 has to be switched off and next positive one thyristor at the positive side has to be turned on, that will be T3. So, T3 will be E2 positive will be, this is T3. So, T3 conduction period is from here. So, we can mark it now with a different color, that will give a clarity. So, let us take green. So, this is the conduction duration for T3. Now, after some time, after T3 is turned on after 60 degree, that is at this point, E3, E1 phase become more negative. So, now the T2 has to be switched off and next thyristor has to be turned on. So, next is T4 at the E1 phase maximum. So, this is T4. So, T4 duration will be, let us mark it with another color. Let us take this color. So, this is the duration for T4. Now, again positive after 60 degree there is a conductor initiation is required at E3. E3 becomes more positive than E2. So, T4 is our next positive side will be, next side will be T5 at the positive side of this one, that is T5. Then last E2 becomes negative, that is from this portion onwards, that is T6, that is T6. So, if you see the sequence 1, 3, 5 top and 4, 6, 4, 6, 2, that is T6, T6 is this one, sorry. So, the next phase will be, so I will just clear this part. So, next part will be, here it is T6, this is T6. So, the sequence if you see T1, T3, then T5, this is T5. T1, T3, T5, T4, T6, 2. This way we have to turn on the, this is the sequence with which we have to turn on the devices. Alpha is equal to 0. Alpha is equal to 0 positive side, negative side at the same point. That is whenever the two adjacent phases just cross equal, that is a point. That is for positive side this is alpha is equal to 0 starts here, for negative side this is the way, and these two are independent. But for symmetry of operation, if you see every 60 degree a thyristor, every 60 degree duration a thyristor is turned on, is turned on. Each thyristor will be conducting for 120 degree. Degree duration. Okay. So, individually we have written the ripple content for alpha is equal to 0 for positive side and the negative side. So, what will be the net output ripple? Net output ripple will be the positive minus negative. If you see instantaneously, you will give the next output ripple, that you can do it. So, if you see the output ripple will have a 6 pulse content. So, in a 360 degree the duration will be, that means every 60 degree you are initiating. So, it is a it is like a 6 pulse waveform. The ripple half frequency will be 6 times the fundamental. How do you do it? The positive side and negative side. Positive side, as you as in the previous as I told you, the positive side, if you see here, that is this portion, that is this portion, this voltage, or this voltage with respect to the neutral here. Let us take this is VA, upper side, this is N, Vn. So, total voltage across the ripple, the instantaneous voltage ripple, this, let us see, this is B. So, VAN, that is a half bridge, positive half bridge ripple minus the negative half bridge ripple. AN minus BN will be the negative is already negative. So, when you subtract it will become again positive. So, AN minus BN is the next ripple content. You can, this you can find out easily. So, output ripple will be the positive ripple minus negative ripple. So, as the alpha is increase for the positive side, the corresponding increase for the negative side also should be increase or symmetry operation. Okay. Now, let us take, this is for highly inductive load. What will happen if it will be resistive load? Or if you, if here also as before, if you do not want the output voltage, you do not want the output voltage, negative portion is not required. We also 3 phase we are using just for some power converter applications where we require large power. So, high voltage is required, but at the same time you do not want the negative voltage, that is firing angle control. We do not have to control in such a way so that output should not go negative. Then what will, then how this can be achieved? See here, we can, let us go to the next page. As before, for the single phase and 3 phase midpoint configuration, we can connect a diode. This is our 1 by 2 E1, E2, E3. See here, if you do not want a negative ripple is not, if you do not want it to appear on the load side, you can put a diode. Okay. Then same like midpoint, you will get into the discontinuous conduction. So, before coming to that one, let us find for a 3 phase fully controlled converter, what is the output voltage ripple, output DC with respect to firing angle. For the 3 phase half bridge converter, we found it is E0 alpha is equal to 1.17 ERMS into cos alpha. This is for the 3 half base. So, we can assume for the fully controlled converter with the inductive load, not with the freewheeling diode. Freewheeling diode is not there. That means we are trying to get both positive as well as negative voltage. It will be for the 3 phase E0 alpha 3 phase fully controlled converter. It will be 2 times with a symmetrical firing angle. For the both the positive as well as negative, it will be 1.17 into E cos alpha. So, this we can easily derive, or we can draw the ripple and we can find the integration also, we can find out that one. Okay. Now, for if we put an output diode, whenever the output voltage ripple goes negative, the load will freewheel through the diode. So, that means the negative portions will be clamped to 0 level across the load. So, this means with the firing angle we can have 0 to positive voltage here. But before coming to the but we require one extra diode here. So, in a similar the same way what we have done in single phase case, can we get away with a diode? Then we have to use a 3-phase semi converter. Before coming to the semi converter, let us find out what is the type of ripple for a 3-phase converter without diode. What is the type of the nature of the output voltage ripple coming across the load. Let us take for a firing angle alpha is equal to 30 for this converter, for the 3-phase converter. So, we will remove this diode for the time being. And we will connect the load here. That is, load is connected here. So, let us see how the output ripple comes, and again we will mark the thyristors. This we know, this is T1, this is T3, and this is T5, 135, then this is T4, T4, then this is T6, and this is T2. Okay. Now, let us draw the output ripple for the 3-phase fully controlled converter. Let us draw the 3-phase voltage waveform E1, E2, E3. This is E1, this is our x axis E1, that is E1. Now, E2. This is E2. Now, E3. E3 will be 240 lagging with respect to E1 or 120 lagging with respect to E2. Okay, we got the waveform. Now, we have the, if we can think about the positive half as well as the negative half. The positive half, the firing angle alpha is equal to 30. That means, we are firing alpha is equal to 30 here. 30. Now, for the T1, alpha is equal to 30 means it starts from here. Probably we will use this is E1. We will use a different color, so that the clarity of the ripple will be clear. We will use red. So, this is the voltage ripple coming across the load when T1 is turned on. Okay, T1. This is T1. Now, at this point, that means we are taking the positive half bridge, 3 will be fired. So, 3 will be means it is here. Here 3. That is thyristor 3. Then here the thyristor 5 will be turned on. This is 5. Similarly, for the negative, when the phase voltage goes negative, the bottom devices T4, T6, T2 has to be switched on. So, let us say when Vy and E2 is negative, that is this is when E2 is negative, that is this portion, the thyristor T6 will be turned on. So, T6 will be, this is T6 portion. Okay. Then after T6, this waveform is the E3 waveform. E3 going negative means T2 will be turned on. So, from here T2 will be turned on this way. At this point, even waveform negative, maximum negative, here T4 will be turned on. So, it repeats like this. This is 4, this is 2 and this is 6. So, we have ripple voltage for the positive and ripple voltage for the negative. So, if you see here, with respect to our mains negative, mains neutral, the positive part we can call as A. The negative part we can call as instantaneous values of the ripple due to the positive we can call as AN. AN is the neutral point, BN. So, the net voltage, output voltage is positive instantaneous subtraction of positive minus negative, that is VAN minus VBN. So, VAN minus VBN will be there. So, the positive, as I told, the positive ripple is here, and the negative ripple is here. So, what will be the net? What will be the net ripple coming across the output? VAN minus VAN. Then instantaneous value is the positive as well negative. If you subtract, the ripple waveform will be like this. So, this will go in a cycle. So, this is 60-degree duration. So, we have the ripple will be 6 times the fundamental. This is the 0. Okay. Now, as the firing angle varies, so this will have an average DC voltage. When alpha is equal to 90 degree, here also it is the output voltage is equal to E0, alpha is equal to 2 into 1.17 into ERMS into cos alpha. So, alpha can vary from 0 to 180 degree. When alpha is equal to 90 degree, the ripple will have equal positive and equal negative. Output DC will be 0. When now we want the output voltage only from 0 to positive, and we do not want the negative excursion. Then I told you that we can put a diode across the load, so that load can freewheel. But one more extra diode is required. So, here also 3-phase fully controlled converter can work as in a semi converter mode. That means 3 thyristor can be controlled, other 3 can be used diode. So that the voltage can go from 0 to positive all the time only. How it will be? Let us see. Again, we want only positive voltage, 0 to positive output DC voltage. So, the bottom converter, the semi converter, the converter we will use diodes. The bottom switches we will use diodes. So, this is the okay. E1, E2, E3. Here is the load. Okay. Now, we have diodes here. The diodes, one advantage of the diode, the moment it is forward bias, it does not require a gate pulse to turn on. The moment it is forward bias, that is, anode is positive with respect to cathode, it will conduct immediately. And as I told before, sorry, we will just correct it. We will redraw once again. So that this is diode, this is diode. Okay. So that the diode will, so here the moment the diode is forward bias, output will quickly, the diode will be forward bias, immediately it will conduct. Now, as I told before, these two can also independently we can control, as the previous case of midpoint conversion during the positive converter during the positive half cycle of the waveform, converter during the negative half cycle of the converter. So, that means we have the E1 here, E2 here, E3 here. Okay. So, the positive side it will be like this, okay. This is our A side, that is A side. To the A side, we will connect the load, okay. Similar way, the diodes are like this. Here, this point will go here, this is called B, this is also B, E1, E2, E3. Okay. This is our neutral point. Load is connected like this. E2, so we will redraw this one. There is E1 from here. So, this is our neutral, 3-phase neutral side. Now, output ripple, total output ripple is the output ripple due to the top thyristor convert, that is VAN, minus VBN is equal to VAB, that is the instantaneous voltage ripple across the load. So, we can consider these two independently and we can find out what is the ripple. Independently means the top thyristor with the firing angle alpha, the bottom diodes with firing angle alpha is equal to 0. So, the net voltage VAB, we know for that VAN will be equal to 1.17 RMS into cos alpha. Okay. What about VBN? VBN is due to diode with the firing angle alpha is equal to 0. So, it is already negative. So, minus of that one will be positive. So, this will be equal to 1.17 ERM, because diode cos alpha is equal to 0, cos alpha is equal to 1. So, the net voltage for the semi converter is equal to 1.17 E into RMS that into 1 plus cos alpha. Okay. Now, in the previous slide, we showed that for a 3-phase fully controlled converter, output ripple is 6 times the fundamental frequency. But let us see what will be the type of ripple for this diode, the thyristor diode configuration. Here we have introduced diode so that output voltage we do not want it to go negative. Okay? If it does not want to go negative means, let us see whether this will happen. That means we can only, with the firing angle, we can have only 0 to positive value. Let us see a typical output voltage ripple for firing angle alpha is equal to 60 and alpha is equal to 90. So, let us draw the waveform for alpha is equal to, that is upper bridge alpha will be firing with respect to angle alpha is equal to 60 degree. So, let us draw the VAB E1, E2, E3 waveform. This is our E1 waveform. Let us draw E2. E2 will be 120 degree lagging with respect to E1. Okay, let us draw the E3 waveform. Now, let us take the voltage ripple due to the diode. Diode will conduct at when firing angle alpha is equal to 0. So, alpha is equal to 0 start any phase, it starts from here, here and here. So, the conductance, so the ripple due to the diode, the negative side is like this. This is the diode. Diode will act as negative side, will always act as a three phase half bridge configuration, three phase half bridge rectifier. So, the ripple is like this. Now, depending on the firing angle, the upper limb ripple will vary. So, now here in the present case we are studying for alpha is equal to 60 degree. So, 60 degree means it will be like this. See, this is the 60 from here to here, then from here it will immediately go here this way. So, this is the, so every 60 degree it starts from here. So, this is 60 degree. Similarly, this is 60 degree. It will come here. So, this is the ripple. This is the AN ripple. This is the VAN ripple and this is the diode, that is the BN ripple. VBN. So, VAN minus VBN, if you instantaneous value, if you plot it, it will be like this. Here if you see, this is the 0 line. Alpha is equal to 0, the ripple exactly comes to 0 line and then switch. But if you see here compared to fully controlled converter, the semi converter ripple is 3 times the mains, but the fully controlled converter it is 6 times. So the ripple content, the ripple content of the current will be much less in a 3-phase fully controlled converter compared to 3-phase semi-controlled converter. That means with the thyristors and diode. So this is 60 degree. Now let us say alpha is equal to 90 degree. Alpha is 90 degree. You can draw it. Then the ripple will be like this. Alpha is equal to 90 degree, this portion goes negative. The moment goes negative, the thyristor and the diode will act as a short circuit. So they are discontinuous. That means output ripple will suddenly be, output is shorted, equivalent to putting a freewheeling diode. It will come here. This is the one. So as the firing angle increases, slowly this the discontinuation period will increase and output voltage will come to 0. So the equation for the output diode and the using thyristor and diode, as I told you, ED0 into 1 plus cos alpha for the semi-controlled converter. Okay. So it will come like this. Now, why we have come to the semi-converter. So many drive application we may not require the output voltage negative. We want only a voltage control from 0 to positive. Then we need not use thyristors, because thyristor, if we use with using thyristor and with alpha control, we can have always 0 to positive voltage. But the problem is with the thyristors, again we require extra gate drive circuit, so it is expensive. Instead of that one, we can do away with diode. That is the purpose. Now, so far we have assumed that the conductions are instantaneous. Okay, conductions are instantaneous, and there is no delay between the incoming thyristor and the commutating thyristor. The moment reverse bias is applied, we assume that the conducting thyristor will immediately switch off, but that is not the practical case. In many practical cases, there is a finite time for turn on and turn off process. So let us see what will happen due to the finite time required for turn on and turn off process. Is there will introduce any problem with the output voltage? Let us study that one now. So we will go to the effect of finite on times. So this is called the commutation process. So far the formulas derived in the previous sections are based on the assumption that the commutation process is instantaneous. Okay. That is, the current switch on and off are instantaneous, but due to the presence of line inductor in the AC supply, the transformer and the SCR circuitry will not permit instantaneous current change. See, even though the thyristor can be instantaneously turned on and turned off, but there will be a finite line inductance, transformer inductance. So where conducting limb cannot a conducting limb cannot switch on or switch off the current instantaneously due to the finite inductance. So apart from the finite turn on and turn off time, the circuit inductance, because of the circuit inductance, the leakage inductance due to the wiring or power circuit bus structure or due to the transformer, there is a delay in the turn on and turn off process. So this can create a decrease, even though the decrease in the output DC voltage due to this commutation overlap. What I mean, turning on and turn off time, they are not instantaneous. There is a period the commutation process goes through. That is called the commutation overlap. Due to that, there can be a reduction in the output voltage. So we will study about that one in the next class.